This video today is going to talk about how to simplify radicals. If you do not have a note taker, you forgot to pick one up in class, a link to a copy of the note taker is included in this post on Edmodo. All right, so the first thing, we have the product property. So this says that the square root of a product equals the product of the square roots of the factors. So that sounds a little bit confusing, but it labels it here in a generic form. It says the square root of AB is equal to the square root of A times the square root of B. So for this example, if you look, we can say since the square root of 4 times 100, even before this, it might look like this, which we're going to do 400. So you can break that down into the square root of 4 times the square root of 100, square root of 4 times the square root of 100. And then you can take the square root of 4, which is 2, the square root of 100, which is 10, and 2 times 10 is 20. Okay, so we're going to work with manipulating these and simplifying these radicals by kind of breaking them up inside and then taking the perfect squares. Okay, so just quickly, I want to say that if this right here, the square root sign, this is called the radical. Just a refresher, hopefully. And underneath what that is the radicand, because you're going to hear me refer to both of them, so I want to make sure that you know the terminology. So the radical and the radicand. Okay, so the other property is the quotient property, and this says that the square root of a quotient equals the quotient of the square root of the numerator and the denominator. Again, generic example right here. It's saying if you have the square root of A over B, that is equal to the square root of A over the square root of B. You can kind of break that into the numerator and the denominator. So if we look at this example, we have the square root of 9/25. This can easily be broken into the square root of 9 over the square root of 25. And then you can go one step further. The square root of 9 is 3, and the square root of 25 is 3 over 5, or 3/5. So, a couple things. First, we talk about these radicals are going to be in simplest form. So I want to just let you know what I expect or what in simplest form is. So they're in simplest form if a couple things happen. Number one, there are no perfect squares. Other than one are in the radicand. Radicand. Same thing. Okay, so yeah, one is always going to be there if you think about it, because 1 times a number is always a number. So we're talking about other perfect squares other than 1. So 2, we want no fractions. And the radicand also. And we want no, hold on, no radicals in the denominator. That says appear in the denominator. So those three things must be true in order for it to be the radicals to be in simplest form. All right, so let's look at a couple examples. How this is going to work, I'm going to do a couple, and then you're going to be left to finish the ones that I did not do for homework. So the first one I'm going to do is number 2. I'm going to kind of, for lack of room, kind of stagger the question. So square root of 50. Okay, when I look at this, I want to break this into 2 numbers, one of which is a perfect square, because then I could simplify that perfect square and leave what's left under the radical. So if I look at 50, the first thing comes to mind is 25. So I'm going to break this down into the square root of 25 and the square root of 2. That law, the product property, says that you can do that. Okay, well now I have to evaluate what I have. The square root of 25 is 5, and the square root of 2 cannot be simplified anymore, so it stays as the square root of 2. So the answer to number 2, simplified, would just be 5 square roots of 2. Next example, number 4. We have 3 square roots of 20. So I'm going to leave this 3 out front because I can't do anything with that yet. And I'm going to think of a perfect square that is a factor of 20. Well, that would definitely be 4. So then we have times the square root of 4 times the square root of 5. Now, if I simplify this a little more, the 3 stays out front. The square root of 4 becomes 2. And the square root of 5 is already in simplest form. So now all I have to do is multiply my 3 and my 2 from out front. 3 times 2 is 6. So my simplified answer would be 6 square roots of 5, I'm sorry. All right, number 6. Negative square root of 108. That negative front is just going to hang out in front, and we're going to bring it down towards the end. When that negative is in front of the radical, not under the radical, those are two completely different scenarios. So we want to make sure we're just going to kind of bring this guy down in front. So I'm going to break this into the square root of 36. Again, if you have to, start working a factor table on the side like we did when we were factoring. Go and see 1 in 108, 2 in 54, 3 in 36. Try to find that highest radical that is a factor of that number. So again, this negative is just going to stay out front. Okay, well the negative comes out front. The square root of 36 is 6, and the square root of 3 is already in simplest form, so it stays as the square root of 3. So my final answer would be negative 6 square roots of 3. All right, one last one on here. I'm going to do number 8. I'm going to do it over here. Sorry, you might want to organize your paper a little better than I am, but so I have the square root of 6 and the square root of 8. The first thing I'm going to do is I'm going to multiply these together and get the square root of 48. And then I'm going to see if I can simplify the square root of 48. It just so happens that 16 is a factor of 48. So the square root of 16 and the square root of 3. And now I can go a little bit further. The square root of 16 is 4. And the square root of 3 stays as a square root of 3. It cannot be simplified anymore. All right, so again, I did a couple examples. Take a minute, finish 1, 3, 5, and 7 on that example 1, and we're going to go ahead and look at example 2. Okay, so we just did the product property. So the next property that we are going to look at is we are going to do example 2, the quotient property. So I'm going to do example 10 with you. So for 10, I have the square root of 18 over the square root of 3. Okay, well 3 on the bottom in the denominator can't be simplified anymore. It already is. So we're going to take a second and work with this square root of 18 on the top and see if we can simplify that a little more. Well, we all know that we can break that down into the square root of 9 times the square root of 2, and this 3 just stays in the denominator. We're not going to do anything with that yet. Okay, well, let's see. Keep going on the top. The square root of 9, I could simplify to 3, and the square root of 2 just stays as the square root of 2, and we have a 3 on the bottom. Well, if you notice, we have a 3 in the numerator and the denominator, so we can go ahead and those would cancel each other out. That 3 and this 3 cancel each other out. They just become a 1, so we're left with the square root of 2 as the answer. Last one on this side, I'm going to look at number 11. We have the square root of 80 over the square root of 45. Now, if you can reduce first, I would always suggest doing that. It just makes your life a little bit easier, and it makes those numbers that you're simplifying a little less complex. So I'm going to go ahead and reduce this, divide both sides by, or top and bottom by 5, and this turns into the square root of 16 over the square root of 9. Well, then we can go ahead. The quotient property says we can break this up to the square root of 16 over the square root of 9, and we all know the square root of 16, I hope, is 4, and the square root of 9 is 3. So our final answer would be 4/3. So just make sure, look when you start, if you can reduce those fractions to make your life a little bit easier, you might as well go ahead and do it. All right, on to the back. So this is a little bit continued, still working with the quotient property. I am going to do 13, and I'm going to change 14 a little bit, and we're going to look at another example. So for 13, we have 8 and the square root of 3/4. Well, we're going to break this up into 8 on the top, right? The 8 would technically over 1, so it's going to go in the numerator. And then we're going to break this into the square root of 3 and the square root of 4 on the bottom. Well, can we go a little further? Sure. We can take the square root of 4 on the bottom. 8 square roots of 3 on the top over the square root of 4 is 2. And now we're not quite done yet. We can still simplify this. These have to be left in simplest form. So 8 divided by 2, this would be 4 square roots of 3 as our final answer. They do get a little bit more complicated, but you just have to stick to the rules that you know about square roots and about fractions. All right, last one. I'm going to change this to square root of 81 times the square root of 10 divided by the square root of 5. Now, before I do this, I am going to look and see if there's anything I can reduce. I can start off by multiplying 81 and 10 and then having the square root of 810, but that's going to be a little bit more difficult. So I'm going to, right off the bat, I'm going to take the square root of 81, and that's 9, divided by the square root of 10 over the square root of 5. So this is 14 right there. All I did was took the square root of 81. Now, numbers under the radicals can be multiplied or divided together. So technically, because we have the square root of 10 over the square root of 5, we can rewrite this as 9 square roots of 2. So I'm going to just note this on the side. Numbers under the radicals can be multiplied or divided. Divided together. Okay, so remember that. It's important to know. All right, so let's look at when we don't have the square root, but we have the cubed root. So these examples, you're simplifying cubed roots of things. So this gets a little bit more complicated because most people aren't familiar with the cube roots like you are with the square roots. So I'm going to list a couple up here. So 1, 8, these are perfect cubes. 27, 64, 125, 216, 343, 512, 729, and 100. 1,000, I'm sorry. These are all perfect cubes. Yes, your calculator can help you find them, but it is less time consuming if at least you know, I would say at least know up to 216. I know that in Algebra 2, most of them require you to memorize up to 10, but for this, I think that if you can get up to, 216, maybe know that 1,000, the cubed root of 1,000 is 10, that might be helpful also. All right, so first I'm going to look at 15. I have the cubed root of 56. Well, 56 is not a perfect cube, so I need to try to think. Again, if you need to, start writing out the factors of 56 and find the highest perfect cube. If you notice, we can split this into the cubed root of 8 and the cubed root of 7. Well, the cubed root of 8 is 2, right? 2 times 2 is 4, times 2 is 8. And I can't do anything with this 7, so this 7 just stays under the radical, and this would be my simplified answer of the cubed root of 56. All right, going to do 18 and 20 with you. Well, 18 is, again, you would just have to memorize this. The cubed root of 1,000 is 10. That was nice and simple. And again, for 19, different color. Actually, I'm going to do 20. I have the cubed root of 750. Well, 750 can be broken down to the cubed root of 125 times the cubed root of 6. And now I could break this down. The cubed root of 125 is 5, and the cubed root of 6 You can't do anything with it, so it stays, and this is your simplified answer. All right, just a couple more examples here, all the way down at the bottom. We're looking at some monomials where we're taking the square root with some variables. So I'm going to do 21 for you. With 21, we have the square root of 32, and that's r squared k to the fourth t to the fifth. So first thing you're going to do, let's write this down, is you're going to simplify the number. So in this case, it would be 32. Then the variables. So also, for each x squared, you can take out an x. So if you have x to the fourth, you could take out x squared. You're basically dividing by 2, the exponent by 2, and whatever you get, you can take out. But if there's a remainder, like look at t5, I divide that by 2. 2 goes into that 2 times, so I can take t squared out, but I have to leave t squared in. So for here, I'm going to simplify 32. I'm going to simplify that to the square root of 16 and the square root of 2. And then the square root of 16 becomes 4 square roots of 2. Okay, so I'm going to back up real quick. So I'm going to pull the 4 out. And this 2 has to stay under the radical. Well, let's say we have r squared, so we can take 1 r out. I'm basically dividing by 2. 2 divided by 2 is 1. 4 divided by 2. Oops, I'm supposed to be taking these out. Hold on. So I took out an r. I can take out 2 k's, k squared. And then with this 5, technically t to the fifth is t squared times t squared times t to the 1. So you can take out 1 here and 1 here. So t squared comes out, and that last t has to stay in there. This is where it gets a little bit trickier, but just stick to the rules. All right, last one, number 23. Square root of 56, x, y to the 10th, z to the 5th. So I'm going to break square root of 56. The biggest square in 56 is actually 4. So 4 and 14. So square root of 4, a 2 comes out. I don't know if I'm going to have enough room. And then the 14 has to stay in. There's nothing I can do with 14. It's as simplified as far as it goes. I can't take an x out because I only have 1, so I'm going to leave that x in there. Divide 10 by 2. I can take 5 y's out. And again, that z, is that z to the 5th? Okay. Divide it by 2, so I can take 2 z's out, but a remainder of 1 has to stay in. Okay, well, we will do, again, finish up all the examples that I didn't do, and we will work with this when I see you in class.